My name is Matt Miller, and this is Lab 4 on oscillations. In this lab, we will observe the motion of a spring as it moves with an attached mass. As a video was provided for our use, we will use Tracker to analyze its motion, and then we will be able to use that data from Tracker to create a computational model to better understand this complex motion. Using Tracker, we'll observe the mass attached to a spring and collect the data to create the computational model. We'll then be able to compare the computational model with the observed model to reveal similarities and/or differences, and we will also compare the energies. Some background info: we will be using Newton's second law to incorporate in updating the position and velocity equations of the mass as it moves through time. We'll also need to use the spring constant, and we will be able to derive that from the period equation. The given information for this problem was the mass was equal to 0.42 kilograms, the length of the spring was 0.7 meters, and at time equals 0, the initial velocity was 0. Here is the tracker data as we observed it moving through time. We were able to attach a point mass to it and track its motion to collect the x and y components of its motion. We then were able to calculate the period of one oscillation. We did this by collecting times from 4 different completions of one oscillation and averaging that to get the period of 1.638 seconds. We then were able to calculate the spring constant, which is 4 pi squared mass over the period, and we found that to be 9.687 newtons. We then could use that. The last variable we needed to solve for was L0, which we now have the spring constant, so we can plug that in to find L0 of 0.2933 meters. Next, we were going to construct our computational model. We set the initial conditions that we were given at the beginning of the problem, setting the mass and the position and the velocity vectors accordingly. We then were able to set G 9.8, the spring constant that we found, to 9.687, L0 to what we have found, and also edited the lines to describe L, which was ball position minus the spring position. We then also updated all the different spring energy equations: the kinetic equation, the gravitational equation, the potential spring energy, and the total energy. We used those energies to construct our computational model, and in our while loop, we were able to set the ball's velocity using Newton's second law and the ball's position using Newton's second law, and also adjusted the remaining energy equations accordingly. And as you can see to the right, this is what our computational model looked like. As the ball moves through time on the spring, all the different energies are recorded in one time energy graph, and the position versus time of the ball is recorded as well. So here's the model. Green is represented as potential spring energy, red as potential gravitational energy, blue as kinetic energy, and orange as the delta change in energy. As you can see in the prediction versus modeled, or the observed versus modeled, the blue denotes the prediction model, while the red is the observed data. You can see the observational is a bit off, given that it is susceptible to drag force and will eventually slow compared to the computational model. First discussion. For your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots. So here you can see all the different energies plotted, and if we write down the energy principle, delta E equals delta K plus the potential gravity and potential spring, they all should equal 0. And that is true because, as you can see, the orange line is delta E and it stays constant throughout the simulation. Second discussion. Using the data obtained in Tracker, make 2 separate estimates of oscillations periods, first by estimating the period of oscillation from x position data, and the second by estimating the period of oscillation from the y. As you can see on the left, the oscillation of the x variable is larger than the y variable. This can be accounted to there being more movement in the x-axis. And we can describe this as being a result of the x direction is affected by gravity and length when calculating period, as when you're calculating the period in the y direction, it is only affected by the spring constant and the mass. Thank you.